Now we come to chapter 6, module 7. In this chapter, we shall apply Fourier transform to solve some partial differential equations. Now we start with example 1. Here we shall solve Laplace equation satisfied by the function phi xy. Laplace equation is given by del 2 phi del x2 plus del 2 phi del y2 equal to 0, where x ranges from minus infinity to plus infinity and y greater than equal to 0. With the boundary condition phi at y equal to 0 is fx, x ranges from minus infinity to plus infinity. Here fx is a known function whose Fourier transform exists, and phi del x, del phi del y all tend to 0 as root over x square plus y square tend to infinity. So here the range of x is from minus infinity to plus infinity. So we shall apply Fourier transform in x to solve Laplace equation together with the boundary condition. For this, let us suppose capital phi x sy. This is the Fourier transform of small phi xy, and which is defined as 1 by root over 2 pi integral minus infinity to plus infinity phi xy e to the power isx dx. Now we multiply the Laplace equation on both sides by 1 by root over 2 pi e to the power isx and integrate with respect to x from minus infinity to plus infinity. Here we note that the integral minus infinity to plus infinity del 2 phi del x2 e to the power isx, this can be simplified. First we integrate by parts so that we get del phi del x e to the power isx, x from minus infinity to plus infinity, minus is integral minus infinity to plus infinity del phi del x e to the power isx dx. Now from the condition that phi x tend to 0 as root over x square plus y square tend to infinity, the first term here is 0, and so we write 0 for the first term minus is, then we integrate this integral again by parts so that we get 0 minus is into phi isx, x ranges from minus infinity to plus infinity, minus is minus infinity to plus infinity integral phi e to the power isx dx. Again, from the condition that phi tends to 0 as x tends to infinity plus minus infinity, this term becomes equal to 0, and so we finally get minus s square integral from minus infinity to plus infinity phi e to the power isx dx, and the integral is the Fourier transform of small phi. So finally we get minus s square capital phi sy. Now using this result, we obtain from the Laplace equation after taking its Fourier transform, we see that the partial differential equation Laplace equation reduces to an ordinary differential equation given by d2 capital phi dy2 minus s square capital phi equal to 0, where y is positive. Again, taking the Fourier transform of the boundary condition phi x at y equal to 0 equal to fx, we obtain capital phi s0 equal to capital Fs, where capital Fs is the Fourier transform of small fx and phi d phi dy tend to 0 as y tend to infinity. So, using these two boundary condition, we can write the solution of this ordinary differential equation as capital phi sy equal to capital Fs e to the power minus mod sy, and after taking the inversion of capital phi, we obtain the solution small phi of the Laplace equation as small phi xy equal to 1 by root over 2 pi integral minus infinity to plus infinity capital Fs e to the power minus mod y minus Isx ds, which is the Fourier inversion of capital Fs into capital Gs. Here capital Gs is the Fourier transform of the function e to the power minus mod sy. Now we have to find the Fourier inversion to obtain the solution small phi xy of the given Laplace equation. Now, before obtaining the Fourier inversion, we first obtain the inversion of capital Gs, which is the Fourier transform of e to the power minus mod sy. So, Fourier inversion of capital Gs is given by 1 by root over 2 pi minus infinity to plus infinity integral e to the power minus mod sy minus Isx ds. Now we break the integral minus infinity to plus infinity into two parts, that is minus infinity to 0 and 0 to infinity, so that Fourier inversion of capital Gs is given by 1 by root over 2 pi into integral from 0 to infinity e to the power minus s into y plus Ix ds plus integral minus infinity to 0 e to the power s into y minus Ix ds. Here this mod s e to the power minus mod s. So, mod s is s when s is positive and mod s is minus s when s is negative. So, that these two integrals are separated like this. So, performing the integration, we find Fourier inversion of capital Gs as 1 by root over 2 pi into 1 by y plus Ix plus 1 by y minus Ix, and that comes to root over 2 by pi y divided by x square plus y square, and which we denote by small gxy. Here y is positive. So, Fourier inversion of capital Gs is equal to small gxy. Thus, phi xy we can find out as phi xy is the Fourier inversion of capital Fs into capital Gs. So, capital Fs is the Fourier transform of small fx and capital Gs is the Fourier transform of small gx. So, to find out the inversion, that is to find out small phi, we use the convolution theorem to write phi xy as 1 by root over 2 pi integral minus infinity to plus infinity small fu into g x minus u comma y du, and we know the form of g x y, so that we substitute that to obtain phi xy as y by pi integral from minus infinity to plus infinity small fu divided by x minus u whole square plus y square du, where y is positive. And this is known as the Poisson's formula for a function which is harmonic in the half plane y greater than equal to 0 and is prescribed at y equal to 0. Here we may note that to satisfy phi at y equal to 0 is fx from this relation, we have to use the relation limit y tend to 0 1 by pi y by u minus x whole square plus y square equal to delta of u minus x. Here delta is the delta function. And the above problem is known as the Dirichlet problem for a harmonic function in a half plane. So, in this example, we have seen that how to apply Fourier transform to solve Laplace equation. In the next two example, we shall apply Fourier transform to solve diffusion equation which is of parabolic type and wave equation which is of hyperbolic type. Now we come to example 2. Here we shall solve the partial differential equation in phi xt given by del square phi del x square minus 1 by a square del phi del t equal to 0, where x ranges from minus infinity to plus infinity and t greater than equal to 0. Here a is a constant and the boundary conditions are phi del x tend to 0 as mod x tend to infinity, and the initial condition is phi at t equal to 0 is equal to fx, x ranges from minus infinity to plus infinity, and fx is a prescribed function and is such that its Fourier transform exists. So, we shall solve this equation by the method of Fourier transform. Here we can see that the range of x is from minus infinity to plus infinity. So, to solve this partial differential equation, we can use Fourier transform in x variable. So, if we define capital phi st as the Fourier transform of small phi xt as root over 1 by 2 pi integral minus infinity to plus infinity phi xt e to the power I sx dx, then as in example 1 we will multiply this partial differential equation on its both sides by 1 by root over 2 pi e to the power I sx and integrate with respect to x from minus infinity to plus infinity. And for the first term, that is del 2 phi del x2, we shall use the integration by parts and the conditions on x to reduce the partial differential equation into an ordinary differential equation, which is given by d capital phi dt plus s square capital phi equal to 0 for t greater than equal to 0. Similarly, if we apply Fourier transform to the condition phi at y equal to 0 equal to fx, then this get transformed to capital phi at y t equal to 0 is equal to capital Fs, where capital Fs is the Fourier transform of small fx. Thus, using this condition at t equal to 0 and solving the ordinary differential equation for capital phi, we obtain capital phi st equal to capital Fs e to the power minus a square s square into t. So, we have obtained capital phi. Now, small phi is obtained after taking the Fourier inversion of capital phi, so that small phi xt is equal to Fourier inversion of capital Fs into e to the power minus a square s square into t. This can be written as Fourier inversion of capital Fs into capital Gs, where capital Gs is the Fourier transform of e to the power minus s square t, and we write capital Gs as e to the power minus lambda s square, where lambda is equal to a square t. Now, let this capital Gs is the Fourier transform of the function small gx, so that small gx we can write as Fourier inversion of capital Gs, and that is equal to, after substituting the value of capital Gs, we get small gx equal to 1 by root over 2 pi integral minus infinity to plus infinity e to the power minus lambda s square minus I s x ds, which is equal to 1 by root over 2 pi integral minus infinity to plus infinity e to the power minus lambda s plus ix by 2 lambda whole square plus x square by 4 lambda ds. Here we have adjusted this power of e in this form, so that small gx is equal to e to the power x square by 4 lambda divided by root over 2 lambda pi integral minus infinity to plus infinity e to the power minus xi square d xi. E to the power minus xi square d xi integral from minus infinity to plus infinity, it can be written in terms of gamma function, and which is equal to root over pi. Hence, gx can be written as e to the power x square by 4 lambda divided by root over 2 lambda. Now, substituting the value of lambda, we obtain small gx equal to e to the power x square divided by 4 a square t whole divided by a into root over twice t. So, with this knowledge of gx, we can find small phi xt from this formula, that is Fourier inversion of capital Fs into capital Gs, by using the convolution theorem, as phi xt equal to 1 by root 2 pi integral minus infinity to plus infinity small fu small g x minus u du. Substituting the value of gx, we get small phi xt equal to 1 by twice a root over pi t integral minus infinity to plus infinity small fu into e to the power x minus u whole square 4a square t du. Now, this problem physically means that it is a mathematical model for the flow of heat in an infinite medium when the initial temperature distribution Fx is known. Next, we come to another partial differential equation, that is the wave equation. So, we solve for small phi, which is a function of x and t, and that satisfies the hyperbolic equation del 2 phi del x2 minus 1 by c square del 2 phi del t2 equal to 0. X ranges from minus infinity to plus infinity and t greater than equal to 0. With the boundary condition phi xt tend to 0 as mod x tend to infinity, and the initial condition phi at t equal to 0 is fx and del phi del t at t equal to 0 is gx. Here x ranges from minus infinity to plus infinity, and fx and gx, they are prescribed functions of x and are such that their Fourier transform exists. As before, we multiply the given partial differential equation on its both side by 1 by root over 2 pi e to the power I s x and integrate with respect to x from minus infinity to plus infinity to reduce this partial differential equation into an ordinary differential equation in capital phi, that is d2 capital phi dt2 minus c square s square capital phi equal to 0 t greater than equal to 0, where capital phi st is the Fourier transform of small phi xt, and we also use Fourier transform to write these initial conditions as capital phi s at t equal to 0 is capital Fs and d capital phi dt as t equal to 0 is capital Gs. Here capital Fs and capital Gs, they are the Fourier transforms of small fx and small gx. Thus, if we solve this ordinary differential equation for capital phi, then we obtain, after using these initial conditions, we obtain capital phi st is equal to capital Fs into cos cst plus capital Gs divided by Cs into sin cst. Hence, small phi xt, which is the solution of the wave equation, can be obtained after taking the Fourier inversion of capital phi st. That is, we can write small phi xt as the Fourier inversion of capital Fs cos cst plus capital Gs by Cs into sin Cs. That is given by half of 1 by root over 2 pi integral from minus infinity to plus infinity e to the power minus is x minus ct plus e to the power minus is x plus ct into fs ds plus 1 by 2c into 1 by root over 2 pi integral minus infinity to plus infinity e to the power minus is x minus ct minus e to the power minus is x plus ct into capital GS by IS into DS. Here we have used Fourier inversion theorem along with cos CST and sin CST written in form of exponential term. So, this first integral can be written as half of f x minus ct plus f x plus ct by using the Fourier inversion, and the second integral we denote this by capital I. If we can find out capital I, then the solution of the given partial differential equation, that is small phi, is completely known. Now we have to find out the second term, that is capital I. To find it, we note that small gz, this is the Fourier inverse of capital GS, and we can write it as small gz equal to 1 by root 2 pi integral minus infinity to plus infinity e to the power minus ISZ capital GS ds. This is the Fourier inverse of capital GS. Now we integrate both sides with respect to z between the limits x minus ct to x plus ct to find integral x minus ct to x plus ct gz dz, this is equal to 1 by root 2 pi integral from minus infinity to plus infinity e to the power minus is x plus ct minus e to the power minus is x minus ct divided by minus is into gs ds. Now note that this term on the right hand side is same as this I, this term. So, instead of this term in the expression for small phi x t, we can substitute, so that small phi x t is equal to half of f x minus ct plus f x plus ct plus 1 by 2c 1 by 2c integral x minus ct to x plus ct gu du. So, this gives the solution for the wave equation, and this is known as the famous D'Alembert solution for one dimensional wave equation. So, in this module we have learned how to use Fourier transform to solve the partial differential equation, and in this module we have solved three very important partial differential equations, that is Laplace equation, heat equation and wave equation by using Fourier transform.